Hello everybody, Root Beer here. We're going to take a look at question number 17 on the 2001 Cayley paper. So that's the multiple choice contest. If you've been following along, you know what's happening. If this is your first video watching for this particular series, we're taking a look at the multiple choice Cayley paper from 2001. You can click the link in the description and get a copy of the contest for yourself. The link will take you to the CEMC website. You can get all their contests, this one as well as the other ones. So specifically, you'll be looking for the 2001 Cayley. So you can try question 17, have a little pause of the video, and then come back and watch my solution here. A, B, C, D, E, F, G is a cube having side length of 2. P is the midpoint of EF as shown. Well, there it is. It's shown right down there, E, P, F, and these hashed lines mean that they must be equal. The area of triangle APB is, okay, so we got a nice triangle right here, but it's sort of in 3 dimensions, and that's not the easiest thing to work with. We're used to our triangles being flat on a plane, and then there's a variety of techniques. If you know side lengths, you can sort of use Heron's formula or the classic 1/2 base times height. That also works. Or if it's on a lattice, you can use something like Pick's theorem. I don't know. But we're not used to having our we're used to having our triangles flat, not weird and slanty. We don't like that. We don't like slanted triangles. So if I were looking at this and I had it on a cube, it's on a diagonal. If I could maybe raise P up or rotate my cube so that P over here is at the same height as AB, I could treat AB as a base. And then all I would need to know is the distance between P and the line segment AB. And get myself an altitude there. So that's an interesting attack plan. Let's see if that bears fruit. So I will draw, as I often do, a copy of the picture again in the notebook. But I'm not going to label, well, yeah, let's label all the points. No reason not to, really. We got the time here. That was E, that was F, so it's going to have to be C and then D here, and then that'll have to be G and H. Okay, so we've got P here, and it splits it up nice and even. And we have AP, or AB, oh, that's not a good line. That's a terrible line. A little better. Okay. And let's just fill this back in. We had D over here. Okay. So, let's see here. We're told the side length, right? Is it 2? Yeah, side length 2. So each of the sides on this cube are 2. That means each of these is 1. We have a whole bunch of 2s and 1s all over the place. Okay. Now, if I were just to consider the line P connected to AB that sort of makes a right angle in the same plane, we're going to make an altitude or height for triangle APB. Okay? So if we were to sort of look at it from above, we'd have sort of P over here, we'd have A up here and B here. Our triangle would look smooshed like this. And that's a triangle we're familiar with. That's a 2-dimensional triangle, and you have a nice little altitude like this. The problem is, this is a top-down view, and that doesn't exactly represent the full length. You'd guess from here that maybe the altitude is 2, but if you look at it from here, the altitude is clearly not 2. So let's figure out the size of that green line, because once we know it, we know AB, our base, is 2. Well, if we look at things from the side, we'll have A and B sort of inhabit the same corner. And we have our triangle will look sort of like this. It'll occupy essentially a diagonal. And that means our altitude is also going to occupy a diagonal line. So we can probably figure out the green line because we know the side lengths of this cube. So this is a side view. This is a top view. So the green line is hypotenuse of a right-angled triangle. Now, if we wanted to be really clever, we'd call this Q, and then we'd drop a line down here, R, and it would be the midpoint of CD, if we wanted to. Let's call the height H. So being the hypotenuse, H squared is going to be the same as 2 squared plus 2 squared. This is the Pythagorean theorem. Should be old hat by now. So that's 4 plus 4 is equal to 8. So H squared is equal to 8. So if we just want 8, we square root both sides. And we can rewrite that as 2 root 2. Or keep it as root 8, however we're comfortable. And so now triangle APB. 1/2 base times our height, which I guess is PQ. So it's 1/2 2 times H. Well, the half and the 2 will cancel each other out. So we'll just be left with H, which is 2 root 2. And that should be the area of triangle APB. And that's what they were asking for in this question. So I guess we should have left it as root 8. And that's answer A. Okay. So that was a nice little question. We had to think in 3 dimensions, whereas we're used to computing areas of triangles in 2 dimensions. All right. So that was a nice little twist. Certainly worthy of question number 17 on the Cayley paper. So in the next video, we're going to, as one might expect, go through question 18 on the 2001 Cayley, and I hope to see you guys there.